Alright, so today I'm gonna be explaining this important paper with the title Graph Random Neural Networks for Semi-Supervised Learning on Graphs. This NeurIPS paper in 2020. We studied the problem of semi-supervised learning on graphs for which graph neural networks have been extensively explored. However, most existing GNNs inherently suffer from limitation of over-smoothing, non-robustness, and weak generalization when labeled nodes are scarce. So we propose a simple yet effective framework, GRAND, to address these issues. In GRAND, we first design a random propagation strategy to perform graph data augmentation. Then we leverage consistency regularization to optimize the prediction consistency of unlabeled nodes across different data augmentations. Extensive experiments and graph benchmark datasets suggest that GRAND significantly outperforms state-of-the-art baselines on semi-supervised node classification. We show that GRAND mitigates the issue of over-smoothing and non-robustness, exhibiting better generalization behavior than existing GNNs. This is an illustration of GRAND with drop node as the perturbation method. GRAND designs random propagation to generate multiple graph data augmentations, which are further used as consistency regularization for semi-supervised learning. Here the augmented features are given to MLP, and we have consistency regularized training. So you add the loss of supervised learning with the consistency. So once you're given a adjacency matrix, feature matrix, and also drop node, drop out probability delta, then the output is the prediction of Z. So we perturb the input, we perform propagation, we predict class distribution, and we compute the loss. Finally, this is what is the representation of Z. So there are two steps in random propagation. First, we generate a perturbed feature matrix by randomly dropping out elements in X. Second, we leverage X tilde to perform feature propagation for generating augmented features. In doing so, each node's features are randomly mixed with signals from its neighbors. So in the first step, there are different ways to perturb the input data. Straightforwardly, we can use the dropout strategy, which has been used for regularizing neural networks. Specifically, dropout perturbs the feature matrix by randomly setting some elements of X to 0 during training. So epsilon is, we draw epsilon from Bernoulli. Dropout makes the input feature matrix X noisy by randomly dropping out its elements without considering graph structures. To account for the structural effect, we can simply remove some nodes' entire feature vectors instead of dropping out single feature elements. First, randomly sample a binary mask for each node. Second, we obtain the perturbed matrix X tilde by multiplying each node's feature vector with its corresponding mask. So X sub I denotes the ith row vector of X. Finally, we scale X tilde with this factor to guarantee the perturbed feature matrix is in expectation equal to X. In the second step of random propagation, we adopt mixed order propagation. So A bar is just the average of the power series of A hats. This rule enables the model to incorporate more local information, reducing the risk of over-smoothing when compared directly with A hat K. And calculating this is computationally expensive because it has a dense matrix. So we compute it by iteratively calculating and summing up the product of a sparse matrix. So each of these augmented data is fed into a 2-layer MLP to get these corresponding outputs. And for supervised loss, you can do like this, but we also add this consistency regularization loss, because in the semi-supervised setting, we propose to optimize the prediction consistency among S augmentations for unlabeled data. So as t goes to 0, the sharpened label distribution will approach a one-hot distribution, and we minimize the distance between zi tilde and zi bar. So therefore, by setting t as a small value, we can enforce the model to output low entropy predictions. But the limitation of this paper is that it's based on homophily assumption. And they did some experiments on PubMed dataset, Site0, Cora. For example, they compared graph attention with their works. You see some improvements. They did ablation study to examine the contributions of different components in graph. For example, without consistency regularization, without multiple drop node, without sharpening, without drop node.